Well, good thing I caught myself early enough. But at least, the document, has the answers too. Okay. So getting back to the picture. All right, so G2 goes to G1, okay, because you can track down G2. It goes to one of the inputs of G1. The other input of G1 comes from G4, so we want to track down G4 as well. G4 takes one of the inputs from G3. G3 is outputting a 1. G4 also takes the input from D, but we don't know what D is. So as a result, we don't know what is the output state of G4. But if you don't know the output state of G4, because that goes into one of the inputs of G1, you cannot say anything about G1 either. So the answer is we only know that the output of G2 is a 1, the output of G3 is also a 1, but we don't know anything else. Yep.
Can we say that G5 is equal to not Q?
G5 is not Q. You can say that, but that's not a part of the answer that I'm looking for.
But it is a definite state.
It is a definite state.
G is equal to Q.
I'm not, well, when I came up with the question, I did not consider that to be a part of the answer. So I will have to kind of think about, how to deal with that. What you said is right, but I was only looking for things that are either a 1 or a 0, but not in relation to something else. Yep. All right. Well, the mic is supposed to be, oh, it is on, except there's no juice. Thanks to one of the students from cisp310 who generously donated a charger as well as the rechargeable batteries. Gotta do this. I think this is the future of community colleges. It's going to be crowd-funded. As if it is not already, right? In the form of tax. Okay, so I think it is on. And is it good? Okay. Yep, there you go. All right. I like your sunshade.
Poker face.
That reminds me of the current Doctor Who doesn't use a sonic screwdriver anymore. Instead, he has a sonic sunglasses, a pair of sonic sunglasses. It's cool. You have to watch it. Okay, so we got the answer of question number 1. The question of number 2 is a little bit more complicated. So question number 2 is using the same diagram as number 1, but everything else is independent. The output pin Q just transitioned from 0 to 1. So we observe Q changing from a 0 to a 1. So I'm asking, state the outputs of all of the other states and the input pins. For example, if the output of G3 is a 0, state G3 equals to 1. If the output of G1 can either be 1 or 0, state G1 equals to question mark. So I'm looking for every single one this time. And I gave you the order of these things as a hint. Okay? Did anyone notice, these are not in order? Okay? But they're in order in a different way. What kind of way is that quote unquote in order with? Back reasoning, right? Okay, so that's exactly why they're in this particular order. Okay, so let's go ahead, and what I'll do is I'm going to copy this into Mousepad so I can work on the answer in Mousepad, and you can keep looking at the picture on this side. Okay, there we go. All right. So this is question number 2, and these are the things that we have to figure out the outputs of. So when we look at the output of G5, it just transitioned from, I cannot remember my own question. It just transitioned from a 0 to 1. Okay, there we go. So it went from a 0 to a 1, which means that the output of G5 is going to be 1. Okay, that's an easy one. Which also means the output of G6 is going to be 0. Very good. Okay. So we go back to G2. Okay, so in order for G5 to be outputting a 1, at least one of the inputs has to be a 0. Okay? And we know that G6 is outputting a 0. Now how do we know G6 is going to be outputting a 0?
Not Q.
Yeah?
It's like not Q.
Well, not
is
Q
one,
is his
not-
name.
I mean, the value will be.
Okay, so Q becomes 1, okay? This is 1. So this one goes back into here, right? But in order for G6 to be a 0, the other one has to be a 1 as well. But do you know that is going to be a 1?
Yes.
How?
Yeah.
How do you know that's going to be a 1?
It has to be.
Has to be to get 1 and 1 to get a 0 from the G6, right?
Yes.
It's more like that.
Okay, so let's go back first. Okay, so we'll put this one as a not known first. Okay, let's go back to G2. What do we know about G2? Q just transitioned from a 0 to a 1, and here's G2. So in order for G5 to output a 1 instead of a 0, one of the inputs has to become a 0. So the question is, which one is becoming a 0?
The G6.
But why would? But then the question is, why is G6 becoming a 0? Okay, remember G5 and G6. If you ignore the rest of the circuit, G5 G6 is its own D flip flop. It's not edge sensitive, but it is a D flip flop, right? How do you change the state of a D flip flop?
Set it.
Do you guys remember the actual label corresponding to this wire and also to this wire?
It's like dash
Recess,
R,
yeah.
dash
One is a slash S,
and
the other one is a slash R. Okay, slash S being a 0 is going to set the flip flop, which turns Q into a 1. Slash R being a 0 will reset the flip flop, turning the Q into a 0. So that is the question, okay? So we know that the input to G5, the top input to G5, is a 0. That one we know for sure as a 0, okay? But that is just the output of G2. So we know G2 is outputting a 0 in this case. Is that okay? All right? So given that, what is going to be the output of G6?
Oh wait, no.
Well, G6 still depends on G3, right? So let's see if we can figure out what is happening with G3. We know G2 is outputting a 0, which is a big deal because a 0 means a lot with a NAND gate. Okay, any NAND gate that is taking at least one of the zeros is going to have an output of 1. So let's track down the output of G2 and see where it goes. It goes into one of the inputs of G3. Okay, so G3 is definitely going to have an output of 1. Is that making any sense? The output of G2 also goes into G1, so G1 is guaranteed to also have an output of 1. What about G4? Okay, let's track down the inputs of G4. One of the input of G4 is coming from G3. Okay, so G3 goes through here and then go into here. And G3 is guaranteed to be a 1. But we don't know what D is.
Question mark.
So it would be a question mark at least for now. Okay, we'll put a question mark here. And then what about G6? Now we get back to G6.
So G6 is fed by G3 and G5.
Yes.
And we have G3 1, G5 1, 1, 1, 0.
Yep, so G6 is going to be a 0, but that's the reason why it is a 0, okay? Okay, what about the clock line? Do we know anything about the clock line?
It fits G2, G3, so it gives 0 and 1.
Hmm?
Maybe anything has to be 1.
It's B1. Just change the word.
Why does it have to be a 1?
Because G2 has to be.
Because G2 needs to have a 0,
Which means it's fitting
with
on
which
a
both
1.
inputs must be 1s. Yep. And what about D?
Question mark.
D is a question mark? Okay, because we don't know what G4 has to output. Let's double check that. Because G4 has to go into G1. Aha, okay, so we know something about that too, because we know G1 has to be outputting a 1, right? Which means both inputs of G1 have to be zeros. So if both inputs of G1 can only be zeros, and one of the input is coming from G4, the output of G4 has to be a 0.
Wait, can't the top G1 be a 1 as well if it's outputting?
Can't.
Yeah, if G1 is outputting a 1, couldn't the top line going into G1 be in?
Okay, in order for G1 to output a 1, one of the inputs has to be a 0.
Which is G2.
But G2 already, oh, you're right. Okay, G2 already has a 0. So we don't know, so there's no deduction that we can apply to clock. But clock goes into 2 places. So clock goes into G3 as well, and G3 has an output of 1. And the other input to G3 is, G3 has 3 inputs. And it has one input that is a 0 already, so which guarantees that G3 is going to be outputting 1. So we don't know, there's no constraint on the other 2 wires. And what about D?
But there's still a constraint on G2 though, isn't there? So clock has to be a 1. So that G2 can spit
Yes.
out a 1.
G2 is outputting a 0, so both inputs
are
of
1.
G2 must be 1s.
So clock has
So
to
that
be a
means
1.
clock has to be a 1. But D also has a constraint too. Because we already know G4 is a 0.
So it has to be a 1.
Yep, so D has to be a 1. So this is the line of reasoning. It's all based on constraints. The first constraint was easy. The first constraint was Q is now a 1. It turned from a 0 to a 1. So the question is, how did it turn from a 0 to a 1? Now there's actually a flip side, a different way to look at this too.
Yeah, just say if Q is 1, that means data 1, clock is ticking 1, and we go from there.
Because that's the behavior of
Of a
a
D
clock
flip-flop.
or edge sensitive D flip-flop. Yep, so that's the other way to look at this. So there are 2 ways to answer this question. One is to start with Q and then work your way back. And then the other way is to remember that this is an edge sensitive D flip-flop and work your way from the clock in the D line forward to achieve that result. So whichever way you use, it's okay. I mean, it's up to you. Sorry?
Or a little of both.
A little of both is fine. Okay, there's no problem with that either. Yep. But in the end, it is based on your constraint thinking. You know, if this is a circuit that is new to you and you don't even know that this is called an edge-sensitive D flip-flop, then you have to work your way back because you're given that one single constraint to begin with. Q is a 1 now. What can make it a 1? Okay, and so you have to work your way backwards. Okay, so that's cool. And what do you think? Why do you think this kind of question is important? How does it relate to, you know, your career, your future career as a computer scientist or a computer engineer? Debugging, I like that. Okay, because debugging, you know, uses the same kind of reasoning. You're working your way backwards to find the source of the problem. Okay, very good. What else? What else, you know, is involved in the what kind of gray area in computer science or computer engineering requires this kind of thinking? Not looking at other people's code, but you're pretty close. Backward, reverse engineering somebody else's, you know, program. You look at the behavior and then you work your way back. Yep, it's called reverse engineering, which is illegal in the United States, but legal elsewhere. Which is interesting because that puts a certain disadvantage to the United States as a country, because, you know, all the other countries, most of the other countries, you know, do not have any law prohibiting, you know, reverse engineering. So that means they can, you know, go ahead and reverse engineer products that are designed and manufactured in the United States. I should write a letter to our dear president and say, well, if you want to generate jobs, this is one way to do it. Relax, get rid of the DMCA and we're good. Okay, question number 3. Question number 3 is a little bit of what we did in the practice test, but it also tries to kind of remind you of the other way to get to the solution. So the first part of the question is relatively easy because we just have to define. Okay, I'm just scrolling everything up so I can actually put the cursor over here. There we go. Okay, so we want to define GI and PI. Okay, this is like textbook stuff, right? So if you had your notes with you, what is GI?
XI.
It's the okay. It's subscript, so technically it is a subscript like that. Okay. What about PI? PI is called a propagation term, and it is
Not XI.
No. You're correct. So I'm actually the first one is incorrect too because the first one would be negating the first one. Yeah, because you have to negate the first one. Otherwise, it is the adder. The subtractor is only different because of that. Okay, because when you did the subtractor homework assignment, you guys remember, right? I said, oh, it's an easy change, especially if you define the P and G terms, using its own abstraction mechanism, then the rest of the circuit stays the same, right? Okay, very good. So this is part A. That's all I'm expecting. Okay, part A is just reciting your stuff from the notes for subtractor. What about part B? Part B is asking you to use the recursive definition, which is this one here, and derive so that you can spell out B2 step by step by expanding the BI terms one step at a time. Okay, so let's see if I can do it like this. Okay, so B2 is G1 plus P1 B1. Okay, that's the recursive term. And then B1 is G0 P0 C0 B0, and then that's the end of it, right? So what you do is you substitute this with this entire thing. So now you go back and say B2 is G1 plus P1, and then in parentheses put in this stuff here. Okay, and then you expand it. Okay, then you expand it, becomes G1 plus P1 G0 plus P1 P0 B0. Okay, the final answer is not important. It's the intermediate steps that are important. Why do you think the final answer is of little value to me? You could have looked it up. It's in the notes, except in the notes it's C2.
Yeah, but what if you want it in terms of X and Y? I would assume. You want it in terms of X and Y, I would assume.
No, this is actually what I need, but if you put it into X and Y's too, that's even better.
Yeah.
What if we use the R of X, Y, and B of X, Y, and then expanded it like that, which is that, but without the G and the B?
Well, in part B, I specifically say use the recursive definition, which is the definition over here.
Which is X.
I did that and then I started out with X.
You can expand it, yeah. If you expand it out, no points will be taken. But this is the minimum answer that I'm looking for. Okay, part C. Part C is a little bit tricky because my original intent is not to include the expansion to X and to the X and the Y terms. So you're really just working with this one to figure out how many gates you will need. So we'll need 1, 2, 3, right? And then we have 4 and 5. So the answer is you will need 5 gates altogether between the AND and the OR gates if we are only using the G and the P and the B0 terms. If you expand it out into the X and the Y's, then you'll be looking more. Yep.
More gates.
But in that case, I'll use that as the reference for your answer. So I'm not looking for the constant of 5. I will look at your answer in part B, and then you'll use that to determine whether you counted the gates correctly or not. So even if your answer to part B is incorrect, I will still be using that as a reference point to determine whether you get part C right or not. Yep.
What if you did it like how many gates you would need if you had X and Y, but your answer in part B was with G's and P's? I like explained it.
Do you have?
Then you probably would explain it too in
Yeah,
part C,
explain,
right?
like,
Yeah. If
why
you
it's
explain it,
not
then it's
easy.
fine. Yeah. As long as I can follow your reasoning, it's going to be okay. Well, as long as I can as long as I can follow your reasoning and your reasoning is good, then it's okay. Yep. Okay, question number 4 is the reversed version of question number 4 in the practice test. Because in the practice test, I gave you a sequence of things and then I asked you what is it actually doing. So this time I tell you what you're supposed to do, and then you have to give me the sequence of signals to get this done. So we'll have to double check. So the answer, the important part of this one is to make sure that you tell me everything about all of the control signals. Okay, so we got A, D. Okay, so I'm just listing out A, D. We have select, we have load, and then we have clear. And clear is just CLR, and then we have clock, which is the clock signal. So all of these things, we need to find out, okay, what should we put into there? The first operation is read from location 45 in hexadecimal. So what you do is you have to specify the address, okay, with the 45, because the address line is what is specifying which location are we dealing with. The D line is not driven by the RAM, okay, so what you might want to put here is being read by the processor, okay, but it's not driven. You don't know what it is because I never told you about what is at location 45. So there's no actual value you can say here, but you might want to say, okay, but what are we doing with the data bus? Well, the process is reading it, okay. So you can say it's driven by the RAM, read by the processor, something like that. The select line has to be a 1, the load has to be a 1, clear has to be a 0, and then the clock can be a 1 or a 0. It does not matter in this case.
In our previous class, I don't think we had clear or clock. Did we have clear and clock? Did we specify those signals? Because if they don't matter.
You mean in the practice test?
Yeah, in the practice test. I don't remember we specifying clear and clock.
Well, the clear has to be a 0 because otherwise the whole thing is just being reset. I'm pretty sure the clock is specified. In this case, the question did say indicate the state of each input port in italic.
It means optional.
In italic. So in this case, the clock can be a 0 or 1. It doesn't really matter. Okay. Okay, let's go move on to the next one. Next, we want to transition to writing to locations 1, 3. No, that's the content we want to write, and then 7A is the location. So 7A goes here, and then 1, 3 goes here. Still has to be selected. Load has to be a 0. Clear has to be a 0. And then clock, it only happens when you have a rising edge, transition. So even if you specify a 0 in the first step, over here you will have to say, it goes from 0 to a 1. Or in some way let me know that you are specifying a transition. Yes?
We have to have the clear on the second line though, right? Because it didn't change states.
You still want to put a 0, well, because it's not changing, you don't have to specify, correct. And you don't have to specify this cell here either because all the operations need that cell to be a 1. So I'm just making it clear that we're keeping those lines as one as a 1 and one as a 0.
If we did like all this the way you had it on the previous test, is that fine? Like
Yeah.
with the steps
Yeah.
instead of having it like a matrix type of thing.
Yes.
Okay.
Yep.
I mean, isn't that specifying it's going to 0 to 1 if you put 0 for the first clock and 1 for the second? So I took
You mean the question mark?
Yeah. I mean, I put 0 and then I put 1. So it
Yes,
just changes.
that will work too. Yep.
Okay.
So then if you put a 0 here, then you can probably just put a unknown here and then put a 1 here. The thing I don't want to see is putting a 1 on the same row, okay? Because if these things are all happening at exactly the same time, then you have a raised condition. because the rising edge is when the information is clocked in, right? But at that moment, is the RAM still thinking it's addressing 4.5, or is it now addressing 7.8? We don't know. So that's why this has to be the next step. This one has to be, it cannot happen on the same line, which implies things are happening at exactly the same time. Okay. Yep.
The way that I wrote it, I did it in steps.
Mhm.
And
Individual
then,
steps.
Yeah, and then each step was basically sub-steps. So I would say, okay, change to 7.8.
Yeah. That would be
and
perfectly fine.
13.
So you're saying you change the address first, and then you drive
Yeah,
the
I
data
did that in
bus,
each
and then
step.
you select the one, and so on. That would be perfect, as long as the order is correct. It will be fine. Yeah, this is only a problem if people use this representation and put all of the changes on exactly the same line. Then the rising edge is going to have a problem because now it has a raised condition. Okay. And the last operation is pretty easy. We can just specify 0x30 for address. Nothing really to specify on D, except that you have to indicate the RAM is driving it or the processor is reading it. We're still selecting it. Load has to go back to a 1. This is still a 0, and the clock does not need a transition. Doesn't have to go back to a 0. So whatever you put here is going to be fine. Okay, you can say a 0, you can say a 1, it doesn't really matter. Because the read operation is not edge sensitive. Is that okay? Alright, cool. Okay, question number 5. Okay, question number 5 is kind of mechanical. More than anything else, it's really just mechanical. 0, 1, 1, 0 plus 0, 0, 1, 1. Okay, so you basically have to follow the same kind of format that I have been using in this class. Okay, so we have this general format. So here we have 0 plus 1 is a 1, and it has no carry to the next digit. And this is just 1 plus 0, which is a 1. 1 plus 1 is a 0 with a carry to the next digit. 0 plus 0 is a 0. 1 plus 0 is a 1. And then 1 plus 1 is a 0 with a carry of 1. 0 plus 0 is 0. 0 plus 1 is a 1 with a leftover carry of 0. So that carry is important. Okay. Now you can either indicate it over here, or you have to indicate it over here. Okay. Or both. Yep. All right. So now we have to figure out the flags. I'm hoping you guys still remember the flags, because we did spend quite a bit of time talking about the flags. So in this case, the carry flag is a 0. The Z flag is a 0. The sign flag is a 1. The overflow flag is a tricky one. Yep.
Is sign flag 1 when the number is negative only?
The sign flag is the most significant bit of the result. So whatever it is the sign flag. The overflow flag is basically saying, okay, is the sign making any sense in an addition in this case? So remember, the overflow definition for addition is different from the definition for subtraction when you look at the gate logic. When you look at the meaning, it means exactly the same thing. The sign is not making sense. So in this case, we have a non-negative number added to a non-negative number, but somehow we end up with a negative number. So the sign does not make sense. So the overflow flag is a 1. Now the L flag is blind. The L flag does not know whether we're dealing with a addition or subtraction. It is just the exclusive OR of the overflow and the sign flag. So in this case, it is a 0 because 1 exclusive or 1 is a 0. Is that okay? All right? No? Okay, question number 6, the last one. See, it doesn't take long. There's still time to go to the whole bit. Okay, so question number 6. So this is actually, this is a masterpiece too. I actually spent a little bit of time to design this and actually make it work in Logisim. Okay, I double check, make sure it works in Logisim before I put it into the question. All right, so all the individual components are familiar. Okay, so let's count the individual components. We got M as a register. We got A, B, C, and D, just A, B, C as registers. We have a multiplier, which was in the practice test. We have an adder, which is also in the practice test. We have a decoder, which is a easier thing compared to a demux. Okay, it's kind of like a demux with a constant one as an input, and that's it. Okay, and then we have constants and a very weird splitter here. The
I
splitter,
didn't see that till the end. Yeah.
and then there's a little splitter here. The splitter splits off only bit 0 out of the address going into the RAM.
Yeah, that was tricky right there.
There's that splitter. Okay, so the splitter is the tricky part. Okay, so what it does, okay, so but we have to look at where the splitter goes, right? The output of the splitter goes into the select of the decoder. In other words, when the least significant bit of the address is a 0, then we are selecting register A. If the least significant bit of the address is a 1, then we are selecting register B. Okay? One of these two is always going to be selected. Okay? All right. So when we clock it, this part here is really just your really basic
Increment.
M for music box. Okay? It's just an incrementing mechanism. Okay? It just keep going incrementing. So the first thing it's going to do is when M is 0, 0, then register A is selected, right? And we are only reading from this RAM here because the load line is, oh, where is that going?
It's a 1.
It is going
It's a
to,
constant 1.
oh, it's a constant one right here, which is shared by multiple components. So we are always selecting the RAM, we are always reading it, okay? And we are always not clearing the RAM because otherwise I would lose the content in RAM. So the only thing we're doing is we're just clocking, okay, which is fine because it doesn't, because we're not specifying any type of write operation, clock or not, doesn't make any difference to the RAM, okay. But what the clock is also going to many other things that are actually important because it's also going into the clock line of register A and register B as well as register C. Except when it goes into register C, there's a little NOT gate here too. So even though the individual registers are all, updating on a rising edge, okay, but when you look at the actual clock signal, okay, when the actual clock signal has a falling edge, C is updated because of the negation gate here. All right, so that's the tricky part. So on the first rising edge, when we are reading from RAM location 0, A is updated. When M is 1, B is updated. Now here's the tricky part. After B is updated, which is a rising edge, okay, so that will leave me enough time for the output of A to go into the multiplier, the output of B also to go to the multiplier. And that goes into the adder. And register C also goes into the adder. The adder will finish its addition and present the result back into the input of register C. But nothing happens until the falling edge. Okay? So the falling edge right after M becomes 1 is going to update register C so it becomes the sum of what it used to be and the product of A and B. In other words, we are multiplying location 0 and location 1, or the values of those two locations, and then add it to whatever is in register C to begin with. And I specifically have a reset initially, which means all registers are cleared to zeros. So then the output here is when clock is 0, M doesn't, so initially they're all zeros. All the registers start with values of zeros because of the reset. When we have the first 1, okay, when the clock first becomes 1, M doesn't change because, let's see, does M change? Yep, M does change. So M goes to 1, and then A goes to 2 because it's reading from location 0. B doesn't change, C does not change either. So they remain as 0. So if you want to put zeros here, that's fine. And then, when we have the falling edge, C is going to be updated because C is always updated on the falling edge.
You scroll down.
Oh,
Thanks.
yeah. So C is always updating on the falling edge, but at this point, because A times B is a 0, 0 plus 0 is still a 0. So on the first falling edge, C is not going to have any visible change, okay, even though it is quote-unquote updated, it's only updated to a 0. And then we have a rising edge, okay? So on every single rising edge, all the registers get updated. So register M gets updated to a 2, register A gets updated to nothing. It is the same as 2 because it's not selected, it's not enabled. Okay, it is B that is enabled this time, which is reading from location 1, excuse me, which has a value of 3. Okay, register C does not update at this time because register C only updates on a falling edge from the perspective of the main clock. So on this falling clock here, register C is now updated. It's updated to a value of 6 because 2 times 3 plus 0 is a 6. Yep.
How is B enabled?
How is
Can you go back to
the diagram?
Yeah.
Yeah, so B is enabled by the decoder, and the decoder is dependent on bit 0 of the address bus.
But is it only when it's bit 4, 5, 6, and 7, and 4 that it's enabled? Because the M depends on the decoder, right? It specifies
The least significant bit of M specifies, which output of the decoder is a 1.
Oh.
And since we only pick out bit 0 out of the address bus, so it's basically odd, even, odd, even. If it's even, register A is enabled. If it's odd, register B is enabled. Yep.
So when M is equal to 2, why do you read from location 1?
When M,
Yeah, it's 2.
okay, so when M equals 2,
Yeah. And B is equal to 3.
because this is presented to be, it can potentially be a race condition because this part is still specifying the old value.
Yeah.
This part is specifying the new value.
Okay.
But since they're clocking at exactly the same moment, right? So that means, the decoder is using the old state of M, and the so this is updated. So these two are updated at exactly the same moment, with the delay of the decoder. Okay, and then on the next rising clock, register M is updated to 3. This is now updated to 4 because that's the memory. That's the content of memory location 2, and this is updated. This is not updated. And then we go to the next clock cycle. And technically speaking, the falling edge is still multiplying. Okay, let me double check the design here. This is always going to be updated. Oh wait, hold on. It's not always updated. Register C, the enable of register C is shared with the enable of register A. So it's only when register A is updated that register C will be updated. So I take it back. So in this case, because register A is updated, register C is also going to be, in the falling clock, register C is also going to be updated. So that is, okay, yeah.
Wouldn't that make the 6 not possible because register is on?
Right. So let's see. Let me double check again. I made a circuit, I made it work, so I just need to retrace my steps. Okay, the enable of C is shared with the enable of A. So whenever A is updated, C is updated, or in the falling edge of that. Okay, and A is updated when M is even. On the rising clock when M is still even.
So wouldn't that mean C is never updated?
Sorry?
Would that mean C is never updated?
Why not?
Because it's always on the falling edge.
No, but the falling edge will happen. So this falling edge is for sure C is going to be updated. It's this one that it doesn't get updated. But then here it will get updated again because over here it should update to a 12 in decimal because it's still updated by A times B plus C. And on this clock here, this is 4, and the 4, this is going to be updated to a, let's see, this is going to be updated to, oh, right here. This one is updated to location 3, which has a value of 5. So we put a 5 here, and then we have a falling edge. But since in this case, register B is the one that is being selected because of the 3, so nothing happens here, so it stays the same. And then on the final clock of 1, this becomes 5. And since the rest of all the locations are zeros, this one gets a 0.
How's your grading going?
Hidden is hidden.
I got 12, I didn't get it this way.
What if the sum, all of them will be the same?
It has to do with the ordering, like when, so what I would be definitely looking at is when the clock goes from 0 to 1, are we updating M? But only on the rising edge, okay? That's what I'm looking for. Between A and B, they should be alternating. So they're not going to be updated each one, at the same time. So I'll be looking at, okay, updating here, they should stagger. And then with register C, it should update whenever register A is updated, but on the falling edge. So after A is updated, then C will be updated in the falling edge. After A is updated, C will be updated in the falling edge. So those I would definitely be looking for. Now, as to exactly what the value is, I can see that there might be a raised condition here, which means A may actually be reading the content of location 1, and that will make it a 3 to begin with, right?
Yeah.
So that means this is going to be a 4, this is going to be a 5. So that will also impact this one here. This will be 20. But you can write 20 because I did not ask for any particular base, so 20 is fine, which is 1 4 in hexadecimal. And then this one is going to be a 6 because it might be reading location 4 instead of location 3 because of the raised condition. But the ordering of the updates would not change. You can see that only the values are changing, but not the order. So you can have this version or you can have the other version. So the trickiest part, I guess, of this question is this little splitter.
So if it looks relatively kind of right, like
Without this splitter.
like we had the vision, we just didn't get it.
The vision was there. There was a lot of vision.
Sorry? Go ahead.
Me? Oh,
Yeah.
so like, it's like you did most of it right. That'd be like 5 out of 6, or.
I haven't decided yet, but basically I will break it down into small components. Like, okay, do you understand how register M works? Okay, register M is the easy one. It updates on every single rising edge. It's just incrementing. Okay, if you get it right, you get full points for that particular portion of the question. Because I usually grade by rubrics, and then each thing I'm looking for has its own line. So you'll be getting like full points for that one. And then the second thing I'll be looking for is when is register A updated. Okay, so when register A is updated, it has to depend. It depends on the decoder, and the decoder depends on bit 0. Okay. Yep.
How many bit wide is that line going from?
That's a good question. How many do you think it should be?
Because the way you're phrasing it sounds like it's 2.
It's a single bit.
No, I meant the other one.
Which other
The
one?
line going to each letter.
the line, you mean this one?
Yeah.
It's an 8-bit line.
So would that make it only on the first six, or it would go on it would only go on the 0 bit then?
Out of these 8 bits, I'm only selecting bit 0 to pass it on to the decoder. That's what the splitter is doing. Yeah, I did not use the splitter to split 8-way and then just pick out the first one. I just ignore the other 7 bits and just pick out bit 0 and say, okay, this bit goes on to the select of the decoder.
If it keeps adding a 1 in its binary, it will make it every other time it's added to it. Well, the switching.
It's only flipping. It's only switching between a 0 and a 1 because it is bit 0 of the address. Okay. Any questions? Any questions about this one?
Yeah, so have you ever like curved a test ever?
I almost always curve the tests.
Oh. Yeah. But is it based on like the highest grade? Or
No. I do not take the highest score because the highest score can be an anomaly. Okay. So basically what I do is I have secret benchmark students, more than one, okay? I have secret benchmark students where I say, okay, these students represent, what I think, a B or B plus or A minus student, should be performing. So I would curve, the whole class so that those quote-unquote benchmark students, once again, more than one and they're secret, okay? Nobody knows, he or she is a benchmark student. So I would make sure that those benchmark students
Not be here. Yeah, they might or might not be here right now.
may or may not be here.
May or may
That's
not be,
correct.
yeah.
Yes,
There's
yes.
at least one here.
Yes, so not to yes, but not to that question. So there can be any number of my benchmark students right here in this class. So basically, I would make sure that the benchmark students would be about where I think they should be, and then the rest of the class would just kind of curve with that.
So how do you know if it's just the first test? Though?
Dude, come on.
Huh?
How do you know if it's just the first test? Though?
Homework. Is there some
Algorithm.
There's homework for one thing. Okay.
Homework.
attendance? What if someone outperforms your benchmark?
Well, the second thing I can also look at is the entire curve of the class, right? So I can look at the entire bell curve. Okay, you guys know the bell curve thing, right? From statistics, I'm hoping. Okay, so I'll just pull up a bell curve so that you guys can see what I'm talking about.
If you do the intent, it's gonna be normalized.
Yep.
No.
So, okay, so look up bell curve, go to images. Okay, there we go, we have a bell curve. So what I usually do is I would say, half the class should be getting B's and C's, okay? More than half the class. The majority of the class should be getting B's and C's, okay? So, some of them will be getting A's and some people may be failing. Now, if I curve the whole thing so that my benchmark students get, a B plus or an A minus, and nobody, ends up getting a C, that's okay. In other words, if everybody is very close to my benchmark students, they can all be getting B's and possibly A's. It's not a problem. I never use C's and D's and F's, to shape the curve. Okay, I only use, somewhere between an A and a B to shape the curve.
So when will these be graded? Like,
Sorry?
When will these be graded? Like in a week or two?
Usually within a week. It depends on the, how much time I have. Yeah, this doesn't sound like a very easy one to grade.
Exactly. Yeah. There are lots of tiny little.
But I'm getting
elements.
pretty good at this, okay? Well, first of all, it involves a lot of actual paperwork. When I say paperwork, it means actual paperwork. So what I usually do is I take this entire pile, unstaple every single one, so I can run the whole thing through a scanner. So now I have an online scanned version of every single test, every single page of every single test. Then I can restaple the whole thing, give it back to you guys for reference. Okay, if you want to toss it away, that's fine. Okay, and then I will start grading. Because once it's online, it's actually easier than the paper form. Because when it's online, I can use Google Drive. And the thing is, if you have a whole bunch of PDFs in the same folder in Google Drive, you can go from one document to the next document using an arrow. And for whatever reason, it can actually maintain the page number of all of the documents. So it's very easy for me to grade just question number 1, go through the entire class, then go back to the beginning, grade question number 2, and then grade question number 3, and so on. I never grade one single person entirely because that's actually a lot harder. Because it's harder to apply the grading schemes consistently if I'm doing it that way. But if I'm grading just number 1 40 times, it can get boring, but it becomes mechanical and consistent. So that's what I usually do is I grade one single question and then I grade another question and so on. It will still take some time, especially some of these questions, is kind of open-ended and it takes a little bit of time to grade it.
That's okay.
So within a week or so, but I'm hoping that by disclosing the correct answers, you guys will get a general idea of, okay, I got most of it right, I got some of it wrong, but most of it is okay. You might want to review as I said, might want to review the syllabus to know where I break the grades. Okay, what is an A, what is a B, what is a C, what is a D, what is an F, because it's not the same with your other classes. Any questions? No questions?
I have a question.
Yep.
On on question 5,
Mm-hmm.
I think it's the oh no, question 4. Yeah, I switched the load, so I said 0 would be. I switched the read and the write.
Mm-hmm.
Would that be like a 3 or a 2?
Okay.
Everything else was right in terms of the process.
Okay, so
It's
if
just
you
that
switch it,
switched.
I will be looking to see whether you are switching consistently. So whenever you specify read, is it always a 0? Do you put it back into a 0 for the last read operation? When you do a write operation, do you switch it to the opposite of the read operation and turn it from a 0 to a 1?
Yeah.
So if you do it that way, there will be a B, which is basically, yes, you definitely demonstrate you understand the concept, this controls the flow, but no, you did not get it perfectly, but it's sufficient to show me that yes, you got it mostly right.
Cool.
Yeah. The worst you can do in that particular case is to make it kind of random, like a 110, which makes no sense whatsoever. That would be a D answer. Yep. Okay. Go ahead.
For question 3,
Mm-hmm.
I did the gates according to the X and Y, but I don't know if I specified it, because it says in the question,
In part
it says
B.
N and OR gates, but I assumed that the P gate itself needed one
Okay.
to make it, so is it fine if I put like total N and total OR?
Okay. I can probably tell from your answer, whether you are accounting for the definitions of the P's and the G's. The P's and the G's are easy because each one requires a single gate, right? So since we in the final equation, okay, let's take a look at the final equation here. So in the final equation, we have all of these terms. So this is one gate on its own, one gate on its own, one gate on its own. This is already done. One gate over here, so we have 4 additional gates compared to the other answer. So it'll be pretty clear whether you counted those additional gates or not. All right. Any other questions? No.